Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is exponential functions. Our objective is to introduce exponential functions, an extremely important mathematical skill necessary for the transient or time-based analysis of DC circuits incorporating energy storage devices like capacitors and inductors. Up until now, all of our previous circuit analysis scenarios have been restricted to resistive components, passive electrical devices that dissipate any power delivered to them as heat. While this served our purposes quite nicely and allowed us to discuss fundamental electrical laws, series and parallel properties, and useful network theorems, other devices exist that are commonly employed in most modern electrical circuits, notably capacitors and inductors. Capacitors and inductors are electrical devices that, rather than dissipating energy in the form of heat, they can both absorb and return a measurable quantity of electrical energy to a system. Capacitors store energy in the form of an electrostatic field between two charged plates. Inductors, in contrast, store energy in the form of a magnetic field in a coil of wire. Both these devices are sometimes known as reactive components, and they can be employed in both DC and AC circuits. Being both a means of temporarily absorbing and returning energy, circuits employing these reactive devices necessarily require more sophisticated analysis techniques than those previous skills we employed in steady-state analysis of circuits employing only resistors. The intention of today's lecture is to discuss the mathematical techniques commonly employed in the upcoming transient analysis of DC circuits. Transient, again, means time-based analysis and concerns itself with sudden changes in voltage and/or current as a function of time, both conditions which highlight the unique characteristics of capacitors and inductors. Fair warning, this is a long lecture and presents some pretty esoteric math skills. Esoteric, by the way, means intended for or likely to be understood by only a small number of people with specialized knowledge or interest. My advice to you is this: get interested in this topic, acquire this specialized knowledge, and get this monkey off your back as quick as you can. Otherwise, acquisition of the upcoming electrical theory making use of these math skills simply will not happen. Pay now and play later, or play now and get hopelessly lost later. The choice is yours. Let us begin by examining the number e and review negative exponents. By themselves, these concepts are readily understood by most mathematically competent individuals, but for some reason, people freak out when you put them both together. Let's not freak out and take a look at them separately before we put these concepts together. The number e, quite like its irrational and transcendental buddy pi, has a unique place in many different natural phenomena, electricity being just one of them. E is a number that can be expressed out to an infinite number of decimal places as 2.71828182846 blah 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 blah. One obtains the value E by memorizing it to a desired degree of accuracy or by recalling it from a calculator. The Texas Instruments TI-89 Titanium Edition Scientific Graphing Calculator, made in China, makes this possible with a keystroke combo. One presses the green diamond key and then the X key, where e raised to the x is written in green above the x key. The calculator then asks to which power we wish to raise e to. For the purposes of just getting the value of e, we raise e to the power of 1, close the parentheses, and press enter. The calculator spits back 2.71828 blah 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 blah, as we'd expect. Note that I've set up my Texas Instruments TI-89 Titanium Edition Scientific Graphing Calculator up in a very specific manner, and I am emphatically recommending you do the same. I detail how to set up the scientific calculator way back in the DC Math lecture, available at the Big Bad Tech channel. Please check out this lecture if you haven't done so already. If you want a quick refresher, here's how I've got mine set up. Display digits float. Angle, degree, exponential format engineering, complex format polar, exact approximate, approximate. If you're displaying different answers than I am, chances are you are doing it wrong or your calculator is set up incorrectly. Now that we all know how to find e to the desired decimal place, let's review negative exponentiation. A negative exponent is when a number is raised to a negative power, as in 10 to the negative third. The negative sign means the base 10 is on the bottom side of a fraction and then it is raised to that power. In this case, 10 to the negative third means 1 over 10, where 10 is raised to the third power. 10 to the third is 10 times 10 times 10, or 1,000. So the expression 10 to the negative third is 1 over 1,000, or in decimal form, 0.001. Another example of negative exponents is 2 to the negative 2. This is asking us to move 2 to the denominator side of the fraction and then raise it to the power of 2. 2 squared is 4, so 2 to the negative 2 is 1 over 4, or the decimal equivalent, 0.25. Try these next couple of examples by yourself. See if you can take them out 6 decimal places. By all means, pause the lecture and try this on your own. Here's the answers I obtained when I entered each of these expressions into my calculator. 3 to the negative 1 is 0.33333. 2.7 raised to the negative 1 is 0.370370. 2.72 to the negative 1 is 0.367647. 2.718 to the negative 1 is 0.367918. 2.7183 to the negative 1 is 0.367877. Finally, 0.271828 to the negative 1 is 0.367880. Even the dimmest bulbs among you should be aware that I just led you by the nose into solving for increasingly accurate representations of the expression e to the negative 1. All we need to do now is just put e in there instead of an approximation of e. To my calculator's best ability, e raised to the negative 1 is 0.36787944171 blah blah blah. Consider y as a function of x being equal to e raised to the power of negative x. Y of x equals e to the negative x. Let's say we're being asked to solve for x equals 1, where y of 1 equals e to the negative 1. You didn't freak out when numbers were raised to a negative exponent, so why freak out now? The Texas Instruments TI-89 Titanium Edition Scientific Graphing Calculator makes solving this expression very easy. One presses the green diamond key, then the X key, where e raised to the x is written in light green above the key. The calculator then asks to which power we wish to raise e to. For the purposes of this expression, we want to raise e to the power of negative 1. Insert a negative sign, which is different than a minus operator, the number 1, close the parentheses and press enter. The calculator spits back 367.879 blah 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 times 10 raised to the negative third power, because we're using engineering format. Expressed without engineering format to the third decimal place, e to the negative 1 will be 0.368. See if you can solve for the following x values. Let's go out 3 decimal places. X equals 2, x equals 3, x equals 4, and x equals 5. By all means, pause the lecture and try this on your own. If you're tracking, you should come up with the following values. When x equals 2, e to the negative 2 is 0.135. When x equals 3, e to the negative 3 is 0.050. When x equals 4, e to the negative 4 is 0.018. Finally, when x equals 5, e to the negative 5 is 0.007. Finally, give this one a shot. When x equals 0. Anything raised to the 0 power is 1, and e is no different. In sequence, e to the 0 power is 1. E to the negative 1 is 0.368. E to the negative 2 is 0.135, e to the negative 3 is 0.050, e to the negative 4 is 0.018, and finally e to the negative 5 is 0.007. Let's plot these results on a graph where x is on the horizontal axis and y is on the vertical axis. As one can expect, when x equals 0, y is 1, and it drops off rapidly as x increases in value. So rapid is this drop that when x equals 5, we can kind of ignore anything past 5 and say it's effectively 0. This assumption, by the way, is not mathematically true because the curve is asymptotic in that it gets super close to 0, but never actually gets to 0, even when x is really large. For example, e raised to the negative 10 is roughly equivalent to 0.00045 nothing, so small we can effectively ignore it. Really, for our purposes, everything interesting happens between x equals 0 and x equals 5. And let's just say at x equals 5, y equals 0. Just take your time and get a feel for the shape of this curve. Trust me, you'll be seeing it a lot. One can also analyze exponential functions in an entirely different manner. What if we wanted to know the specific x value that yielded a specific y value, as in 0.5 equals e to the negative x? which exact x satisfies this condition? Given e to the negative 0 equals 1 and e to the negative 1 equals approximately 0.368, we might expect the x value that satisfies this condition to be between 0 and 1. Just guessing, I'm saying it's maybe about 0.7-ish. To answer this question with any degree of accuracy, one needs to perform the inverse function on both sides, known as the logarithmus naturalis, or natural log, abbreviated as ln. The natural log of e to the negative x yields negative x. To perform the natural log operation on the Texas Instruments TI-89 Titanium Edition Scientific Graphing Calculator, one needs to press the light blue second key and then x, which has the function ln written in light blue above it. Enter 0.5, close the parentheses, and press enter. The calculator spits back negative 0.693. Divide both sides by negative 1. We're left with x equals 0.693, super close to our earlier estimate of 0.7. Now that you've got an introduction to a basic exponential function, let's try these examples on for size. For the set on the left, given these x values, see if you can solve for the resultant y values. See if you can take the answers out to 3 decimal places. For the set on the right, given these y values, see if you can solve for the x values that satisfy these conditions. Remember, to solve for the desired x values, you'll have to use the natural log function. Again, see if you can take these answers out to 3 decimal places. By all means, pause the lecture and try these on your own. If you're tracking, you should have obtained the following results. For our first set on the left, e raised to the negative 1.5 yields 0.223. E raised to the negative 2.5 yields 0.082. And finally, e raised to the negative 4.3 yields 0.014. Note e raised to the negative 4.3 is super small. Like I said earlier, all the magic happens between x equals 0 and x equals 5, so 4.3 being super close to 5 is very, very small. For our second set, e to the negative x happens to reach 0.75 at an x value of approximately 0.288. The function e to the negative x equals the value 0.25 at an x value of approximately 1.386. And finally, the function e to the negative x reaches the value of 0.125 at approximately x equals 2.079. Let's compare some results from the first set with that of the second. Notice that e raised to the negative 1.5 is roughly 0.223, which is super close to 0.25 at x equals roughly 1.4. These results seem to agree with our expectations. Again, you should be getting a feel for this function. Note it starts at 1 and then rapidly drops off a cliff. It obtains a value of 0.75, or 3/4 of its start value, at x equals roughly 0.3. It obtains a value of 0.5, or half its start value, at x equals roughly 0.7. It obtains a value of 0.25, or 1/4 of its start value, at x equals roughly 1.4. And it obtains a value of 0.125, or 1/8 of its start value, at just past x equals 2. Like I said earlier, all the magic does happen between x equals 0 and x equals 5, but if you think about it, all the really, really important magic happens between 0 and roughly 2. Between x equals 0 and x equals roughly 2, our function goes from a start value of 1 to 1/8 its start value, and then from x equals roughly 2 to the remaining x equals 5, it slowly degrades to effectively 0. Because we'll be using this function so frequently, it might be a recommended practice to include evaluations of e to the negative x at specific x values on your cheat sheet. Rounded to the thousandths place, they are at x equals 0, y equals 1. At x equals 1, y equals approximately 0.368. At x equals 2, y equals 0.135. At x equals 3, y equals 0.050. At x equals 5, y equals 0.018. And finally, at x equals 5, y equals roughly 0. Alright, let's step this up a notch. What happens if I put a constant in front of the exponential function, as in y of x equals a times e to the negative x? The answer is not much. Just multiply the result of the exponential times the constant a. For example, consider the expression y of x equals 6 times e to the negative x. What does y of x equals 6 times e to the negative x look like if we plotted it for x values from 0 to 5? Big surprise, it looks exactly like e to the negative x, only it starts at 6 and drops to 0 by x equals 5. Let's say we're being asked to evaluate this function at x equals 1.9. Substitute x equals 1.9 into the expression. E raised to the negative 1.9 is roughly 0.150. 6 times roughly 0.150 is roughly 0.897. Too easy. We can also solve for unknown x values given known y values. For example, consider the question, at what x value does 6 times e to the negative x equal 5? Answering this question necessitates we isolate the exponential function on one side of the equal sign by dividing both sides by 6. 6 cancels out, and we're left with 5/6, or 0.833, equals e to the negative x. Take the natural log of both sides. The natural log of 0.833 equals approximately negative 0.182. Get rid of the negative signs on both sides. We're left with x equals 0.182. If you want to, you can check your work. 6 times e raised to the negative 0.182 equals 6 times 0.833, which equals 5. It makes sense. Try these example expressions on for size. For the set on the left, given the x value, solve for the resultant y value. For the set on the right, solve for the x value that yields the specified y value. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. When x equals 0.8, 12 times e to the negative x equals roughly 5.4. When x equals 1.8, 8 times e to the negative x equals roughly 1.3. Finally, when x equals 2.2, 24 times e to the negative x is equal to roughly 2.7. For our second set at roughly x equals 0.693, 12 times e to the negative x should equal 6. This agrees with our earlier observations. 6 is half of 12, or 0.5. At roughly x equals 2.079, 8 times e to the negative x should equal 1. This again agrees with our earlier observations. 1 is 1/8 of 8. Finally, at x equals roughly 0.693, 24 times e to the negative x should equal 12. This again agrees with our earlier observations. This all makes sense. 12 is half of 24, or 0.5. Finally, if we were to plot any of these functions for values of x equals 0 to 5, they all look astoundingly similar. All functions start at the specified constant value, and they rapidly drop to 0 by x equals 5. You should be arriving at some level of familiarity with this function. The general use function, a times e to the negative x, starts at some constant a value and then rapidly drops to 0 by x equals 5. If I was to qualify the general use function a times e to the negative x use only words, I'd call it start at a and rapidly decay. Can you dig this on every level that I do? By all means, pause the lecture and stare at this without blinking until you do. We can also analyze this function in a different manner. What if we were asked to solve for the x that satisfies the following condition? 0.6 equals 1 minus e to the negative x. This necessitates algebraic manipulation and the use of the natural log function. Get the exponential by itself by subtracting 1 from both sides. We're left with negative 0.4 equals negative e to the negative x. Get rid of the negative signs on both sides. We're left with 0.4 equals e to the negative x. Take the natural log of both sides. We're left with negative 0.916 equals negative x. Get rid of the negative signs on both sides of the equation. We're left with x equals 0.916. Let's see if you can try these example problems on for size. For the first set on the left, given these x values, solve for the resultant y values for the function 1 minus e to the negative x. For the second set of example problems on the right, given these y values, solve for the x values that satisfy these conditions. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. For the first set on the left, at x equals 1.3, 1 minus e to the negative x equals approximately 0.727. At x equals 2.8, 1 minus e to the negative x equals approximately 0.939. Finally, at x equals 3.5, 1 minus e to the negative x equals roughly 0.970. Notice at x equals 2.8, the function has already grown to roughly 0.94, and at x equals 3.5, we're at roughly 0.97. This is to be expected. All the rapid growth occurs pretty early, in this case between x equals 0 and x equals roughly 2. Then it just slowly creeps up to 1 between x equals roughly 2 and 5. Past x equals 5, we can say 1 minus e to the negative x is effectively 1. At x equals roughly 0.357, 1 minus e to the negative x equals 0.3. At x equals roughly 1.609, 1 minus e to the negative x equals 0.8. Finally, at roughly x equals 2.303, 1 minus e to the negative x equals 0.9. Note I've written out the algebraic steps necessary to obtain these values. However, they're all using the same techniques. Get the exponential by itself by subtracting 1 from both sides. Get rid of the negative sign on both sides. Take the natural log of both sides. Get rid of the negative sign of both sides, and you obtain the x value that satisfies the given condition. Because we'll be using this growth function so frequently, it may be a recommended practice to include the evaluations of 1 minus e to the negative x as specific x values on your cheat sheet. Rounded to the thousandths place, they are at x equals 0, y equals 0. At x equals 1, y equals 0.632. At x equals 2, y equals 0.865. At x equals 3, y equals 0.950. At x equals 4, y equals 0.982. And finally, at x equals 5, we're assuming that y equals 1. Let's step it up another notch. The growth function can also be multiplied by a constant a. The general purpose growth function looks like this. Y of x equals a times 1 minus e to the negative x. Note that the constant a is multiplied by everything inside the parentheses. If you wanted to, you could distribute the constant a into the expression as follows, where y of x equals a minus a times e to the negative x. Either version works, your choice. Consider the expression y of x equals 6 times 1 minus e to the negative x. If you're so inclined, you could also write the same expression as y of x equals 6 minus 6 times e to the negative x. Let's say we're being asked to evaluate this expression at x equals 1.1. Substituting 1.1 into the equation yields 6 times 1 minus e to the negative 1.1. E to the negative 1.1 is 0.333. 1 minus 0.333 is 0.667. 0.667 times 6 is roughly 4.003. Let's try this in reverse. At what x value does 6 times 1 minus e to the negative x equal exactly 4? Divide both sides by the constant 6. Subtract 1 from both sides. Get rid of the negative signs on both sides. Take the natural log of both sides. And get rid of the negative sign on both sides. We're left with x equals 1.099, super close to 1.1. What does the function y of x equals 6 times 1 minus e to the negative x look like if we plotted it for x values 0 to 5? Big surprise, it looks like 1 minus e to the negative x, only it starts at 0 and rises to 6 by x equals 5. Try these example problems on for size. For the first set on the left, given these x values, solve for the resultant y values. For the second set on the right, given these y values, solve for the x values that satisfy these conditions. By all means, pause the lecture and try these examples on your own. If you're tracking, you should have obtained the following results. When x equals 0.7, the function 12 times 1 minus e to the negative x yields a value of approximately 6.041. At x equals 1.8, the function 8 times 1 minus e to the negative x yields a value of approximately 6.678. At x equals 2.3, 24 times 1 minus e to the negative x yields a value of approximately 21.594. For our second set on the right, the function 12 times 1 minus e to the negative x obtains a value of 10 at x equals roughly 1.792. The function 8 times 1 minus e to the negative x obtains a value of 5 at x equals roughly 0.981. The function 24 times 1 minus e to the negative x obtains a value of 10 at roughly x equals 0.539. Again, I've illustrated the algebraic steps necessary to obtain these values, but it's all the same techniques. Get 1 minus e to the negative x by itself by dividing both sides by a constant. Get the exponential by itself by subtracting 1 from both sides. Get rid of the negative signs on both sides. Take the natural log of both sides. Get rid of the negative signs on both sides, and you obtain the x value that satisfies that given condition. Finally, if we were to plot any of these functions for values of x equals 0 to 5, they would all look astoundingly similar. All functions start at 0 and rise to the specified constant value by x equals 5. 12 times 1 minus e to the negative x starts at 0 and grows to 12 over a span of x equals 0 to x equals 5. 8 times 1 minus e to the negative x starts at 0 and grows to 8 over a span of x equals 0 to x equals 5. And finally, big surprise, 24 times 1 minus e to the negative x starts at 0 and grows to 24 over a span of x equals 0 to x equals 5. Notice how the function 24 times 1 minus e to the negative x in blue gets to a value of 10 at x equals roughly 0.539. Much sooner than 12 times 1 minus e to the negative x at red. This again makes perfect sense. Given both functions grow from 0 to either 12 or 24 in the same span of x equals 0 to x equals 5, the one growing from 0 to 24 will hit 10 a lot sooner than the one that needs to grow from 0 to only 12. Really, the only thing the constant has done is change the vertical span that needs to be accomplished in the horizontal span of x equals 0 to x equals 5. You should be arriving at some level of familiarity with this general purpose growth function. The general use function a times 1 minus e to the negative x, or if you're so inclined, a minus a times e to the negative x, starts at 0, then rapidly grows to constant a by x equals 5. If you think about it, the growth function a times 1 minus e to the negative x is kind of like the evil twin of the rapid decay function a times e to the negative x reflected in a horizontal mirror. We're left to ponder at which x and which y values do these two functions cross. You have the skills to answer this question. When does a times e to the negative x equals a times 1 minus e to the negative x? You should be able to solve for a corresponding x and y value. Let's first determine the y value. Start by getting rid of the constant a. It's on both sides of the equation. We're left with e to the negative x equals 1 minus e to the negative x. Get the exponentials on both sides of the equal sign by adding e to the negative x on both sides. We're left with 2 times e to the negative x equals 1. Divide both sides by 2. We're left with e to the negative x equals 0.5. This means these two functions intersect midway at y equals 0.5a. It makes sense. Given symmetric decay and symmetric growth between 0 and the constant a, it stands to conjecture that these functions would meet in the middle. To determine the x value, we have to take the natural log of both sides. These two functions cross at roughly x equals 0.693. All right, let's step it up one more notch. What if the variable x wasn't x, but rather t, as in time? This doesn't change our game too much. Consider our general purpose decay function, y1 of t equals a times e to the negative t, evaluated at t equals 0, 1, 2, 3, 4, and 5 seconds. Additionally, consider our general purpose growth function, y2 of t equals a times 1 minus e to the negative t, also evaluated at t equals 0, 1, 2, 3, 4, and 5 seconds. As one might expect, the general purpose decay function, a times e to the negative t evaluated at these times, yields the following data. At t equals 0 seconds, it has a value of 1a. At 1 second, it has a value of 0.368a. At 2 seconds, it has a value of 0.135a. At 3 seconds, it has a value of 0.05a. At 4 seconds, it has a value of 0.018a. And at 5 seconds, it has an effective value of 0. Similarly, the general purpose growth function, a times 1 minus e to the negative t, evaluated at the following times, yields the following data. At t equals 0 seconds, it has a value of 0. At t equals 1 second, it has a value of 0.632a. At t equals 2 seconds, it has a value of 0.865a. At t equals 3 seconds, it has a value of 0.95a. At t equals 4 seconds, it has a value of 0.982a. And finally, at t equals 5 seconds and beyond, it has a value of 1a. Again, big surprise. The decay function goes from a to 0 over a span of t equals 0 to 5 seconds, and the growth function goes from 0 to a over a span of t equals 0 to 5 seconds. All we're doing is plotting them as a function of time now. Whether you plot these curves as function of variables x, t, z, b, or p, these curves really don't change, the shape of which should now be burned into your retinas. And if they aren't now, they will be soon. Let's add yet another twist to our increasingly twisted general use functions. What if we were to introduce yet another constant into our equation? Let's say this constant is tau, which is written kind of like a pi symbol that was playing a little close to a train track and lost one of its legs. Our general purpose decay function now looks like this. y1 of t equals a times e to the negative t over tau. And our general purpose growth function now looks like this. y2 of t equals a times 1 minus e to the negative t over tau. Note e in both cases is being raised to negative t over tau. If you want to, you can circle this ratio to make this relationship explicitly clear. Think of everything inside this bubble as that negative power to which e must be raised. Let's say our constant a equals 6 and our constant tau equals 5 milliseconds. And just for the heck of it, let's say we're being asked to evaluate both functions at time t equals 5 milliseconds. Let's evaluate the decay function first. Substitute in our constants a and tau. Then substitute in our time of interest. Negative t over tau is 5 milliseconds over 5 milliseconds. This ratio resolves itself to 1. 6 times e to the negative 1 is roughly 2.207. We can do the same thing for the general purpose growth function. Substitute in the constants a and tau, and then substitute in the time of interest. The ratio t over tau is the ratio 5 milliseconds over 5 milliseconds, which resolves itself into 1. 6 times 1 minus e to the negative 1 is roughly 3.793. Can you dig it? Tau really hasn't changed anything. It's just another constant we're added to our equation. Additionally, you'll note at the time t equals 5 milliseconds, the summation of these two values yields our constant 6. This is to be expected given these functions are in effect the evil twins of one another. Let's see if we can try these example problems on for size. Given the function y1 of t equals 12 times e to the negative t over tau, and tau is assumed to be 3 milliseconds. See if you can evaluate this expression at t equals 1 millisecond, and again at t equals 4 milliseconds. For our second unrelated function, y2 of t equals 24 times 1 minus e to the negative t over tau, where tau is assumed to have a value of 2 milliseconds. Let's say we're being asked to evaluate this expression at t equals 500 microseconds, or 0.5 milliseconds, and again at 1.2 milliseconds. By all means, pause the lecture and try these on your own. If you're tracking, you should have obtained the following values.